Okay, so first of all, I'd like to thank the organizers for inviting me to give a talk here. So I thought I would tell you about a couple of topological systems which are a bit different from the ones that you've been hearing about. So one of them is a magnetic system where the spin wave bands have Chern numbers. Okay? Therefore, they have some kind of topological properties. The other one is a Josephson junction of 3 wires. And that also, it turns out that the bands of the Adhip bound states have Chern numbers. That also has some consequences. So the spin wave, the Magnon work was done with Ranjani Sheshadri, who was a PhD student. And the Josephson junction work was done with Oindrila Deb, who was a PhD student, and Krishnendu Sengupta, who was here last week, I guess. He's in the Indian Association for Cultivation of Science in Kolkata. So the plan of the talk is as follows. So the first talk will be about the spin system. So it's a spin system on a Kagome lattice, and I'll discuss the phase diagram of it. And then I'll show you that in one of the phases, the Magnon bands have Chern numbers. Okay? And then one of the consequences of that is that you get something called the thermal Hall effect. The second part of the talk will be about Josephson junctions of 3 superconducting wires and the Estes-Josephson effect there, where the topological aspect, Berry curvature, directly plays a role. And then something called Shapiro plateaus, which is an interesting thing that happens, but it's not directly related to the Berry curvature, but I'll tell you about it anyway. And these are the references for these two parts of the talk. Okay, so this couple of slides are really for the students, so I'll just rush through them. So topology basically is a branch of mathematics where we study properties which don't change if you make some small changes in the system. And if you can define an integer which remains the same under those small changes, it's called a topological invariant. So this is very bare bones kind of statement. I'm not talking about symmetries or anything right now. Now, if there's a topological invariant, because it's an integer, it will not change if you make small perturbation in the system, because the only way an integer can change is if it jumps from one integer value to another. So small perturbations cannot make a big jump in an invariant. So a couple of examples of topological invariants. So the number of times you take a point on a plane, let's call that the origin O, and you take a closed curve in the plane, then the number of times the closed curve winds around that origin in the, let's say, anti-clockwise direction is a topological invariant. It's called the winding number. So there's some examples of winding number +1, -1, 0, and then very complicated curves where you actually need a mathematical formula to calculate what the winding number is. Then in 3 dimensions, there's another topological invariant, which is the number of times the surface of one sphere, let's say the red sphere, which I'm just showing by some dotted lines because it will be too confusing to show the entire surface of the red sphere. The number of times the red sphere wraps around the blue sphere is a topological invariant. And it turns out that this is actually related to the Chern number, which I'll talk about later. Okay, so now the concept of Berry curvature. So suppose you have a 2-dimensional system with translation invariant Hamiltonian with a certain number of bands. So translation invariance means that the energy levels and these wave functions of the momenta kx and ky. Then you define the Berry connection as follows. So this is in a particular band which is labeled by n. So the x component of the Berry connection is this derivative gradient of psi in the kx direction, psi dagger del psi by del kx. You need an I to make this real, and there's a y component of a, and then you take the curl of this, okay, which you can relate to the wave function derivatives in this way, and that's called the Berry curvature. Then the Chern number is given by the integrated Berry curvature. You integrate this over the entire Brillouin zone. So this turns out to be an integer. Now, if the wave functions have 2 components, then you can really think of this Chern number as the wrapping number of one sphere around another. Okay? Because you can think of 2-component wave functions as defining a point on a sphere, and then this basically tells you how you're taking a point on the sphere, of kx, ky to a point on the sphere defined by the wave function. But we'll study systems where the wave functions have 3 components, and then you don't have such a simple geometric picture of what this Chern number is. Yeah.
Easy way to understand why we can.
Yeah, I can tell you about this later. So there's a way of mapping between a torus and a sphere which maintains this Chern number. So you can understand it that way. Okay, now what's a topological system? So it basically has the following properties, that the different bulk bands should be separated from each other by some finite gaps. So you should not have any touching between different bands. And then one or more of these bulk bands should be characterized by some topological invariants, which are non-zero integers. If a band has a invariant equal to 0, then it's not a topological band. And then very importantly, there are states at the boundaries of the system which contribute to transport, heat transport or electronic transport. And then there is a bulk boundary correspondence which relates the bulk bands to the states at the boundaries. So the number of boundary states should be related in some simple way to the topological invariants of the bulk band. Okay, so now let me tell you about the first system, which is a spin system. So it was recognized a few years ago that there are spin systems in 2 dimensions which have spin wave bands which are gapped and which have non-zero Chern numbers. So this was probably one of the earliest papers which proposed models with this property. So we have studied a different model where you have anisotropic ferromagnetic interactions between nearest neighbors. So you have spin halves, and then the interactions are of the type XXZ. Okay, so you have SX plus SY plus some delta times SZ. Okay. So anisotropic ferromagnetic interactions and a Zielinski-Mori interaction between nearest neighbor sites on a Kagome lattice. So it turns out you need all of these things. I mean, you need Zielinski-Mori because it breaks time reversal invariance, and you need a Kagome lattice, otherwise it doesn't quite work. So now in the Kagome lattice, so there's a picture of a Kagome lattice. The unit cells are triangles. Okay, so we label the unit cells with some integers, with some vectors n, which are labeled by 2 integers, n1 running this way and n2 running that way. And each triangle has 3 sides, which I'll call an, bn, and cn. And this is actually a finite system, which is also important for us. So later I'll show you that you have edge states which run along the 2 edges, the upper edge and the lower edge. And we deliberately took a system where the 2 edges look different. This one looks like, okay, this one is a flat edge and this one has this ups and downs. But it turns out that when it's in the topological phase, the number of states at each edge is the same. Okay, so now the Hamiltonian. So as I already stated, it has 2 terms. One is ferromagnetic interaction, which is anisotropic. So the XX and YY interactions are equal. The ZZ interaction has a different strength, which I'll call delta. And there's a minus sign overall, so it's ferromagnetic. And then there's this Zielinski-Mori interaction, which is A cross B. So it's just between nearest neighbors. A cross B dot the unit vector along Z. Okay, so this kind of thing is allowed on a Kagome lattice. Okay, it's not allowed on, say, the square lattice, for instance. Okay, so let's suppose we set this j equals 1. So then we just have 2 parameters to play with, which is one is this anisotropy delta, and the other is this Zielinski-Mori interaction d. Now to get started, we looked at a model where the sites have spin s instead of spin half, and looked at the largest limit, because that's the usual way you start studying a spin model. You look at the largest limit and then you do Holstein-Primakov transformation and look at spin waves. So that's what we did to start with. Let's see. The Zielinski-Mori, but it has a, let me see. It's got sigma x, sigma y. So why does this break time, does it break time reversal invariant? But it's got Sx, Sy, right? Yeah, I'll have to think about that. Okay, so that was not the correct statement, but it breaks inversion symmetry. Okay, so the Hall-Stein framework of transformation goes as follows. So if at a particular site, if in a classical ground state the spin points in the z direction, then the three components of the spin can be written like this in terms of this Hall-Stein framework of bosons. And this first expression is exact. The second expression is only valid in the largest limit. There is an exact expression which reduces to this if S is very large. And these A's are bosons, so bosonic operators. So then you write the Hamiltonian up to second order in the bosonic operators, and then you diagonalize it to find the spectrum of excitations, the magnons. Okay, so this is the classical phase diagram. Yeah, it breaks inversion symmetry, not time reversal. So there are 5 regions. So this is delta in the x direction and T, the Dzieloszynski-Mori in the y direction. So in this region, the spins all point, let's say, all point up or all point down. Okay, so that's the classical ground state. Then in this region, the spins point this way, right? So they are all pointing in the x direction, let's say. It could be any direction in the xy plane, but they all point in the same direction. J is ferromagnetic, yeah, right. I put a minus J in front. And then in 3 and 4, these are kind of chiral, so the spins around the triangle turn by 120 degrees. And they have the same sense of turning in all the different triangles. So that's 3 and 4. Turns out the 5th phase is kind of very complicated. The spins are not even coplanar. We can point in 3 arbitrary directions in space. And this is the hardest, we found this to be the hardest to study in spin wave theory. Anyway, the most interesting phase turns out to be phase 1, where all the spins point up or all of them point down. So the classical ground state is really trivial, and there's, if you just looked at the classical ground state, you would not imagine that there's anything interesting in this system. But then if you look at the spin wave spectrum, then you find that there are 3 bands. There have to be 3 bands because the unit cell has 3 sites. And 2 out of these 3 bands have non-zero Chern numbers. Okay, one of them has a 0 Chern number and the other 2 have non-zero Chern numbers. And depending on which band has Chern number and which one has positive, which one has negative Chern number, turns out that this phase actually has 4 subphases within it, okay, which are indicated here. So phase 1 is really topological, right? So it has 4 subphases where the different magnon bands are separated from each other and have different Chern numbers. And the transitions between these subphases occur on these horizontal lines. D by J is minus root 3, 0 and root 3. So I'll show you a picture of the Chern numbers in the next slide. So it turns out that if you're in this phase and you look at a infinitely long strip, so finite width but infinitely long, like I showed you in the beginning, this kind of a system, infinitely long this way and 2 edges, then you discover that there are edge states which lie at either the top or the bottom edge, which lie within the ith band gap, and the number of such edge states, meaning number of edge states with a particular value of the momentum along the edge, is related to the Chern numbers of all the bands below that in this way. So the number of edge states for the ith lying within the ith band gap is equal to the absolute value of the sum of the Chern numbers of all the bands below that. Okay, so here's a picture. So here, this is for the case when delta is 2 and d by j is 2 by root 3. So it's one of those 4 subphases that I showed you. So the top band, okay, so first of all notice that all the bands are gapped away from 0. Okay. Then the top band has a Chern number of -1, the middle band has Chern number 0, and the bottom band has Chern number +1. And there also, this picture also shows the edge states. So you get edge states. So between these 2 bands, for example, between +1 and 0, in that gap you have an edge state along the bottom edge, which has this dispersion. So this is all plotted as a function of k along the edge. Okay. So you have an edge state on the bottom edge. So this, I mean, you should really think of this as the same curve because of periodic boundary conditions. And there's also an edge state on the top edge. The number of states at each edge is +1. which is the same as the number of the absolute value of the number of total Chern number below this band gap. And then in this gap, you have a top, you have an edge state at the top and an edge state at the bottom. Once again, the number of edge states at each edge is 1. It's equal to the sum of the Chern numbers below. So it turns out that depending on where you are in this phase diagram, this picture of which band has Chern number +1 and -1 moves, right? So the example I showed you was, I think, somewhere here. If you move here, then the top one has the opposite Chern number, the bottom one has the opposite Chern number. The middle band is always 0 Chern number. And also when you cross those phase transition lines, then pairs of these bands touch each other. So when you cross one of those lines, these two will touch each other. You cross another one of those lines, these two will touch each other, and so on. So those are the topological phase transitions. It turns out that Berry curvature leads to something called the thermal Hall effect. So the thermal Hall effect is the following thing, that if you apply a temperature difference along some direction, you get a heat flow or energy flow in the perpendicular direction. So imagine that you have these two edges of this semi-infinite strip and you apply a temperature difference between those two edges, then you will get a heat flow along those edges. And so now this thermal Hall conductivity, kappa xy, has a very complicated expression. It depends on the temperature explicitly here, but also there is a temperature dependence hidden in all this. So what are all these different functions? So one is the Berry curvature, B of k. And then there is this function C2 of the Bose-Einstein distribution of these magnons. And C2 is this complicated looking function. So this was all derived in this paper. Yeah, Li2 called polylogarithm. Now because all these bands are gapped away from 0, this will go exponentially to 0 as you go to very low temperatures, as e to the power minus the smallest, minus the gap from 0 up to the lowest state. So here's a plot of this kappa xy, this thermal Hall conductivity, as a function of temperature. So let's look at the lower one first. So as a function of temperature in those 4 different topological phases. So this is a plot of the kappa xy versus temperature. So as I said, at very low temperature this goes to 0 exponentially fast, but as you increase the temperature, these 4 bands, they have some, they show some dependence of kappa xy on temperature, some monotonic dependence. You can also look at the dependence of this kappa xy on this Joloshinsky-Moria parameter d at certain temperatures, and you find this kind of a picture. So it's kind of interesting that every time you cross one of these phase transition lines, the sign of kappa xy suddenly flips from plus to minus. Of course, I mean, it can't be really discontinuous, so it has to go through 0, but in most of these phases, for the most largest regions in these phases, kappa xy is a particular sign which depends on which subphase that you are in. Okay, so let me summarize this part. Okay, so we have studied a spin system on a Kagome lattice, and we found that there are 5 different phases. One of these phases is Magnon bands, which are topologically non-trivial. I mean, 2 of them are topologically non-trivial, they have non-zero Chern numbers. And there are edge states which are related to the Chern numbers. The edge states give rise to a thermal Hall effect. Now an important thing here is that the thermal Hall conductivity is not quantized in this system. This is a bosonic system and they vary continuously with the temperature and other parameters. So unlike an electronic system, unlike the quantum Hall system, there is no quantization of the Magnon Hall conductivity. Nevertheless, it's a topological effect because as you saw, the expression for it has the Berry curvature appearing in it. Okay, so now let me tell you about the Josephson junction of multiple superconducting wires. So it was realized about 4 years ago that a junction of 3 or more superconducting wires may have Andre bound states, so these form bands, and these bands may have a non-zero Berry curvature as a function of the superconducting phases. So we'll see how this comes about. And this is the kind of important paper which started all this. Now, in the earlier part of the talk, spin waves, you had a band which was where the energy was a function of kx and ky. So here, we are just talking about a junction of different wires. So there is no kx, ky, but what you have instead are the superconducting phases, the pairing phases in the different superconducting wires. And those play the role of kx and ky. It turns out you need at least 3 wires to meet at a junction to have an interesting effect and to have a Berry curvature. If you have only 2 wires, it doesn't give you any of these effects. If you have a junction of 4 wires, then you can have Andreev bound states which form wild points, because then you have 3 different phases to play with. So it's like having a 3-dimensional system, and you can get wild points where the Andreev bound state bands touch each other. Okay, so if you're interested, you can look at this paper which discusses junctions of 4 wires. But my talk will be basically about 3 wires. So this is the system that we have in mind. So there are 3 superconducting wires, and then there's a small region in the middle which we model as a normal region. But the electrons or holes coming along these wires can get reflected from these regions, from this normal region, or transmitted. So something coming along one can get reflected back or transmitted to the other 2 wires. And so this junction is characterized by a scattering matrix, S. Now, so there are two pieces to this. One is there's a scattering matrix here, which is a normal scattering matrix. In other words, an electron coming there can get reflected as an electron or transmitted as an electron. On the other end, the superconducting wire eventually goes up to some lead, and at that junction, which is not shown here, between the superconductor and the lead, you can have Andreev reflection. So an electron going up there can get reflected as a hole, or vice versa. And that, the Andreev reflection is characterized by this parameter A, which is given by this, where E is the energy of that electron or hole, and this E has to lie inside the gap, because the entire effect that I'm talking about here is for states which lie inside the superconducting gap. So E has to lie between minus delta and plus delta, where delta is this superconducting pairing and 2 delta is the superconducting gap. Okay, so so there's a compact way of figuring out the energies of the Andreev bound states. So for a system of 3 superconducting wires, you introduce a diagonal matrix, okay, whose 3 components are e to the I phi 1, e to the I phi 2, e to the I phi 3, where phi 1, phi 2, phi 3 are the superconducting pairings on these 3 wires. And let's say the pairing amplitude, the magnitude is the same in all the 3 wires for simplicity, but the actual pairing is this magnitude times e to the I phi I. Now this also is a phase, and then you find that the Andreev bound states and the corresponding electron wave functions are given by this eigenvalue equation. Okay, so the S matrix at the junction shows up here, the 3 phases show up here, and the energy shows up here. And so you have to solve this equation self-consistently, because this A here also involves E. So this was actually first derived by Binneker in a very, very important paper. So this is actually for the case of S wave pairing in all the 3 wires. If you have P waves in some of them, then it changes a little bit. Also, we have suppressed the spin label, so you can get slightly different formulas for the P wave case for spin up Andreev bound states and spin down Andreev bound states. Okay, so now you can solve this eigenvalue equation, and we obtain 3 bands because there are 3 wires, and so there are 3 bands for spin up quasi-particles and 3 bands for spin down quasi-particles. So let me label these bands as n sigma. So n is 1, 2, 3, and sigma is plus or minus, up or down. Now it turns out that these energy levels of these Andreev bound states only depend on the differences between superconducting phases, phi 1 minus phi 2 and phi 1 minus phi 3. Because if you shift all the 3 phases by the same amount, then the Andreev bound state energy will not change. So you can hold, let's say, phi 3 fixed and just vary phi 1 and phi 2. So then you have a kind of 2-dimensional system, right, which is labeled by phi 1 and phi 2. And so this then plays some same role as the momentum kx, ky of a genuine 2-dimensional system. So if all the bands are gapped, we can define the Berry curvature and then the corresponding Chern number. Okay, so here's the Berry curvature matrix, which is very similar to the expression that I wrote earlier, except that the derivatives are now with respect to the superconducting phases rather than the momentum. Now this is a real antisymmetric matrix, and it turns out you can show that in this matrix, every column and every row has to add up to 0. So that comes from some very simple principles. For example, the fact that this matrix doesn't change if all the phases are shifted by the same amount will tell you that all the columns have to add up to 0. Okay, so now if you have a real antisymmetric matrix with this property that all columns and all rows add up to 0, then you can see that if you had only 2 wires, this matrix has to be 0. Okay, so with 2 wires you cannot get a Berry curvature. With 3 wires you can get a Berry curvature, and there will be, for a 3 by 3 matrix with these constraints, you will have only one real parameter. Okay, now just to contrast what happens for time reversal invariant and time reversal breaking cases, we studied what two kinds of scattering matrices. One was a completely symmetric matrix. So it turns out time reversal symmetry just means that S is also symmetric. And we took a really symmetric matrix where all the reflection amplitudes and transmission amplitudes are same between all the wires. And it turns out this still allows you 1 degree of freedom. So you can label this by some lambda, where lambda is, you can imagine, is the strength of a barrier sitting at the junction. The other case we studied is a randomly generated unitary matrix, which is not symmetric and therefore does not satisfy time reversal symmetry. Here is the matrix. This is really randomly generated. I had nothing to do with this. My computer produced this. Now for the symmetric case, this is a picture of the Andreev bound state. So it turns out one of the bands sits exactly at the edge of the gap, right? Plus delta or minus delta. And so there are only 2 interesting bands, which are this and this, positive energy and negative energy. So these are the energy levels, and now if you calculate the Berry curvature, you can see that there are 2 places where it's peaked, positive peak and negative peak, which are actually these regions where, so if the energy is changing very fast with phi 1 and phi 2, you can imagine that the Berry curvature will be large in those regions. The total Chern number which you get by integrating all this is 0. So it turns out that's a general result. If you take any symmetric S matrix, you can get large Berry curvatures at different points in this. I'll call it the Brillouin zone, even though it's phi 1, phi 2 instead of kx, ky. You can get Berry curvatures which are large in certain regions, but the total Chern number has to be 0 in any band. Here's a similar picture for the asymmetric case, that randomly generated S matrix. So again, one of the bands happens to sit exactly at the band edge, but then the other 2 bands are inside, strictly inside the gap. And here there's only one place where there's a large Berry curvature. And actually here it's not possible to guess where this is by just looking at the bands. You know, you don't really have points where they're coming close to each other. But if you calculate the Berry curvature, you do find that it's very large somewhere. And the total Chern number here is not 0, it happens to be -1 in the negative energy band. The sum of the Chern numbers over all the bands has to be 0. So it's -1 here, +1 here, and the flat band has 0 Chern number. Okay, so now if you look at the Josephson current, you have to really rush through this. So there are these Josephson equations. One is that the time derivative of the pairing phase is related to the voltage applied to that wire. And then the Josephson current in wire I is given by this expression. So there is a familiar, first of all, there is this Fermi-Dirac distribution of the Andreev bound states. That depends on the temperature. We are going to work at 0 temperature. And then there is this derivative of the energy with respect to phi. So this is the thing that you are familiar with. The current is proportional to the derivative of the energy with respect to superconducting pairing. The new thing here is that you get an extra term which depends on the Berry phase. So this is like an anomalous term appearing in the current, which is depends on the Berry phase times the time derivative of the phase. Okay. And so this is the new thing that can appear if you have a system with 3 or more wires. So then if you apply some, so in the AC Josephson effect, if you apply some constant voltages, you find that the first term in the Josephson current oscillates in time, this one, because phi is a periodic variable, so as you go across the Brillouin zone, this del E by del phi will average to 0. But the second term doesn't have to add up to, doesn't have to integrate to 0. And you can look at something called the transconductance, which is a very interesting effect. So let's say you apply a voltage only to wire 1 and no voltages to wire 2 and 3. So you discover that you can get a current flowing in wire 2. Okay, so you have a current in one wire when you apply voltage to a different wire. And if you now integrate that current over the phase, superconducting phase, which is constant, then you get something which is proportional to the Chern number. Okay, so here's a picture. So this is the transconductance current as a function of phi 2, and you can see that it has a peak exactly where same values of phi 2 where you had peak in the Berry curvature. Since I've run out of time, very quickly let me just tell you about the Shapiro plateau. So the idea is that you take an RC circuit with superconducting wires. So this is the picture of the circuit. So there's an R and C in parallel between every pair of superconducting wires. Then you have some complicated looking equations which I have to skip. Now it turns out that the normal Shapiro plateaus, when you just have two wires, is that you have an energy which is proportional to cos phi. So you get a Josephson current which is sin phi, which is well known, right? The Josephson current is proportional to sine of the phase difference. And then if you look at you apply, so you actually apply a voltage, but what you really measure more easily is the current. So let's say the current has a constant piece plus an oscillating piece with some frequency omega. Then you find that the voltage has a DC component which shows steps and plateaus as a function of the DC part of the current. So the DC part of V1 has plateaus as a function of the DC part of I1. Now typically you only get one or two plateaus if you had just two wires, but in this 3-wire system, because the energy is such a complicated function of the phases, you discover that the energy is many Fourier components as a function of the pairing phases, and so you get a multitude of Shapiro plateaus, right? You get well-defined plateaus at some integer multiples of h bar omega by 2e, which is a standard Shapiro effect, but you also get plateaus at half odd integer multiples of h cross omega by 2e. And there's actually, in principle, you can get plateaus at any rational multiple of h cross omega by e. Alright, so the summary of this part, and this is the last slide, is that a Josephson junction of 3 superconducting wires is a topological system where the Andre bound state bands have Berry curvature and Chern numbers. The system has transconductance, so applying a constant voltage to one of the wires can give you a current in the other wires. And the integral of the transconductance over one of the superconducting phases is equal to the Chern number multiplied by this constant. And then you can have Shapiro plateaus appearing in a plot of the time averaged voltage versus the time averaged current, DC part, and the current in one of the wires varies periodically in time. And in principle, the plateaus can occur at any rational multiple of the driving frequency. So you can in principle get what is called a devil's staircase of voltage versus current, and that's the reference. Okay, thank you. Yeah.
So when you had this Chern number for this junction case, in one of the value was fractional half.
No, Chern number was only.
Can you go back to that slide?
Chern number was always an integer.
Here.
So this case, the total Chern number was 0. It turns out the integration here gives you +1 and -1, but they add up to 0. Here the Chern number was -1.
Yeah, we're going to go to the next slide. Next. Yeah, here the last. No, that is something else. So C.
No, the Chern number is.
So if you go to the last, C minus, C plus, and C. Oh, okay. I thought it is half or something.
No, it's not half. This is a very complicated notation. One of them refers to, let's see, the minus refers to spin down, +1 refers to the band, one of the 3 bands, 1, 2, and 3. This is the positive energy band. And 1, 2, this is the Berry curvature between wires 1 and 2. The Berry curvature actually is a complicated object here, right? Because it depends on the band label, the spin label, and between which two wires you're calculating it.
That's like a non.
Not really. Band, but I won't call it non-abelian actually. Yeah, it's a 3-level system, but it's
because like curvature or something like that. If you go around it, you come back to the same state. That will be the. Here you are actually coming back to another state as you go around it.
I'm sorry, I didn't say that right. This is a particular band. This Ij refers to the superconducting pairing phases, phi I and phi j. So, okay, so in the pairing phase space, phi 1 and phi 2 space, you come back to the same state but with a different phase. It's still abelian. Still abelian.
In the first part of the talk, the thermal conductivity,
right.
Where does the existence of edge states come into the picture.
Yeah, so
mean-
that's kind of implicit in this. So the way you would measure this is that you take this strip and apply a temperature difference between the top edge and the bottom edge. And then you measure the heat current flowing along the strip.
Because in
So
that
that's-
expression,
So that's, yeah,
pk need not integrate to an integer.
pk.
The,
pk integrates to an integer because that's a Chern number. But you have this
no,
complicated
it need not. I mean, there could be a system where bk doesn't integrate to an integer. Nevertheless, this can be non-zero.
No, bk is a Berry curvature, so it always has to integrate to an integer in a particular band. But
No,
this,
no,
this integral is
it-
not zero because the C2 is a very complicated function of the energy.
No, it could integrate to 0. Plus
Oh, okay. You're right. So bk could integrate to 0 and you're right. Yeah, that's true. So bk could integrate to 0 without this thing integrating to 0. Yeah. But it turns out that, yeah, that's a good point actually. In fact, that happens in the C equals 0 state. So this is a band with total Chern number equal to 0, but at different points you have different values of B. So anyway, when we calculated this, this is the sum over all the bands. So we did take all the bands into account regardless. So this only involves the Berry curvature, so we took that into account. We didn't look at the Chern number in this calculation.
Yeah, Diptiman, I have similar question. So, if you have, so do you have a H state in this case? I mean, like
In the
you have a H state, right?
in this case, yeah.
So why? So if you sort of take out this activated part, e to the power some gap, will you not get a quantized?
No, but you can see this formula is a very complicated looking formula, right? You have this Bose-Einstein distribution appearing there, and then there's a function C2 of this function.
Yeah.
So you can't. There's no simple way of removing the activated part. Also, the activated part is different at different points in the band, right?
Okay.
So I mean, you probably mean take out the smallest possible value of the gap. Yeah, but even if you did that, I don't think you don't get a quantized value.
Okay.
But this is what the plots look like, this kappa xy, and you can see that they simply don't look like constants times any overall factor.
Any more questions? If not, let's thank Mr. Diptiman.